Alright guys, so today we're going to talk about functions in or of several variables. And so last time, or the last few videos, or the last section, we talked about functions. Let's say a function that was vector valued. So we were taking values from the reals and we were sending it into R2 or R3, the plane or the space, let's say R3. So now what we're going to do is kind of reverse it. So we're going to now have functions that we're going to take elements in R2 and we're going to send it to R. Meaning that you're going to grab or R3, but we're going to focus on R2 because those are the ones we can actually plot the graph of. So it's much easier to deal with them, or not much easier, but it's more pleasant, I suppose. The ideas are all the same anyways. So you're going to take an order pair x comma y of real numbers, and you're going to be assigning it a value, let's say z, so the next coordinate, which is going to be a function of x and y. So that is going to be the idea of what we're going to be doing. So the first question you ask when you have a graph or a function is, can I graph it? And whenever you are in R2, sure, if you make this R3, well, that becomes a little bit more complicated, meaning we don't do that. Of course, functions can take any number of variables, and as I said, for us, it's going to be usually 2 variables. But I just want you to know that you can have more. All right, so let's take a look at a graph just real quick. So let's try to graph one of them. So let's say f of x is going to be, I don't know, the square root of, let's say, 4 minus x squared minus y squared. So something like that. You kind of have an idea that when you have x squared and y squared added together, it's going to have something to do with circles. So let's go ahead and take a look. So the way that you want to do this, well, firstly you want to determine the domain of this function. Whoa, f of x and y. Well, there should be f of x, y. And otherwise, there's no dependence on y implied there, and we do want to have a dependence on y. So let's go ahead and take a look at an idea once we have the domain. So the domain of this function, for it to be real valued, of course, is the set of x comma y's in R2, such that this right here, which is going to be 4 minus x squared minus y squared, is going to be greater or equal than 0. So that this square root is defined. Now, if you write this a little bit more detailed or solve for it, let's say, what you end up having is that you have that 4 is greater or equal than x squared plus y squared when you add x squared and y squared on this side, but it's probably nicer to write it like this. So if you look at it in the R2 plane, what you have is that the domain of this function, now just in the xy plane, is going to be the interior, well, not only the interior, the interior and the boundary. So you're going to have the whole circle of radius 2 is going to be the domain of your function. So what that means is that you can only have those possible values. So now we got to figure out when x comma y are equal to 0, it's clear that this function is going to attain its maximum. Just from observation, we're going to learn how to actually calculate that later in the semester. But if you have x comma y equal to 0, you get that the function is going to be taking the value of 2. So the maximum value is 2, and the minimum would be whenever x squared plus y squared would be equal to 4. So you get 0 here. All right, so that would be all around the boundary of this circle. So that then gives me an idea of what kind of values of z I'm going to be obtaining. So I know the domain now. I know that x and y are going to have to be between -2 and 2, and they're going to have to satisfy that x squared plus y squared are going to be less or equal than 4. And then I also know that the function itself is going to be taking values between 0 and 2, which is rather useful for us to graph it. So now that we have that in place, let's try to figure out how to graph it. And I'm going to move over here, so give me 1 second. I'll be right back. So to do this graph, what I'm going to do is I'm going to introduce the idea of a level curve. So I told you that the values that the function would take would be between 0 and 2. So I'm going to start looking at what happens when the function takes the value of, so I'm going to call it z, is equal to 0. So when z is equal to 0, and I'm calling z the f of x, y, then what I have is that this equation is satisfied. Now, whenever I square both sides, I get that 4 is equal to, when I add these guys on this side, but we already did this same idea when we computed the domain, so I'm not going to be too careful. So that level curve is going to be the circle of radius 2, so just the circle. All right, so let's plot that, and probably it would be a good idea to plot it here. So let's erase this one, and let's start plotting in the three-dimensional space. All right, so let's plot that in 3 dimensions. So your x coordinate, y, and z. And you're going to go to -2, let's say there, and +2. Then you're going to go to more or less the same. I'm going to try to draw the circle there. All right, so that's pretty reasonable. So that's my circle of radius 2. So 2 here, 2 here, -2 here, -2. So that's going to be that, and that is going to be called a level curve. So then I can move and say what happens when z is equal to 1. That's a little bit, should have given myself a little bit larger radius so I can start going on integers. Probably will be better to look at, it will be good to look at a 3/2 at some point. Oh well. Let's go ahead and take a look at that. So if z is equal to 1, I plug 1 there, and I put the square root of 4 minus x squared plus, minus y squared. Don't change your signs. You square on both sides, you get 1 is equal to the square root of, not square root, I squared it already. Let me erase that square root. I should make a compilation of the times when I get angry at myself for making a mistake and the faces I make. That would be interesting. Anyways, so I'm going to add the x squared plus y squared on both sides, and I will obtain this, and then I'm going to subtract 1 on both sides. So I'm going to have 4 minus 1 is going to be 3. So that's going to be a circle of radius square root of 3. So to plot that, you're going to go up by 1. Let's say here is z equals to 1. I'm going to go up by 1, and you're going to consider that plane that is 1 unit above. Okay? And what you're going to do, and by the way, the level curves, you can also draw them in just R2, in which case you would have had the circle of radius 2 would be here. So let's make this one with this color. And now with this color, we're going to make the circle of square root of 3, which is 1.6 something, if I remember correctly. So the next one will be there. So, and you can label them by saying z equals 1 with colors, then z equals 0, sorry. There's an extra equal there. And then you could go to the next step. But when I try to draw it here, so we're going to have a circle that is going to be above this one by 1 unit, and the radius is going to be smaller. Wish me luck. So it's going to be like there. Let's draw the plane so I can put. This is where I get in trouble. So I'm going to have a plane there, which is going to be at z equals 1, so a little bit higher. And on that plane, I'm going to go ahead and draw a circle that is going to be going in this direction a little bit less. Let's do 1/2 of it, or 1, so roughly there. So there, I'm going to go to 1.5 I'm using. So it's not quite accurate, but I'm going to go here. Then from here, 1.5 roughly would be here. And here, I'm going to go very, very accurate. You can see, right? So there. So more or less there, I'm going to have my other circle. that will go above that one. When I draw it, I think it looks great, and then I step back and I look at it, I'm like, well, it could be better. It's okay. So now we could do another one. We could do another point, z equals to, the last one we said was 2, and at that point we're going to have that x squared plus y squared is going to be equal to 0. And so that's going to force x and y to be just 0, so it's going to end up being a point here. So that would be the z equals to 2. So in between there's going to be other circles. As you can see, every level curve is going to be a circle because you're going to have something of the form x squared plus y squared equals something else. So you're going to end up having a lot of circles. So I'm not going to do that actually. I'm going to just mark that point as I already said, and I'm going to try to complete the graph. So the graph is going to be this side looks much better. This one is a bit wonky. But it's going to be where every cross section is going to be a circle, it's going to be a hemisphere. It doesn't look too bad. Okay, I'm not an artist, I'm a mathematician, so we'll leave it at that. So what you get is that this function gives you the upper half of a sphere, so a hemisphere. All right, so let's go ahead and look at another function, and then we're going to stop right here. The next video will be about limits and derivatives. But derivatives are interesting because now you have two variables. No, there's no implicit differentiation. It's going to be a little bit different. Anyway, so I'm going to go ahead and draw another one, erase everything, give you another graph, and we'll stop the video right there, and we're going to start a new one right after. All right, so we're going to look at this function here. And again, the idea of the level curves is very useful, so we're going to start with that. Now, the domain for this function is going to be the entire plane, because there's nothing that can go wrong here. There's no zeros in the denominators. The function can be evaluated for any pair x comma y. So we're not going to deal with the domain right now. We're not going to worry about that as it's everything. And then the range is also going to be, it's going to be greater or equal than 0, but then from 0 to infinity. So you don't have much information or much to worry about. The range is what really matters for us, as you notice, because that's going to give you the values that you can use for your level curves. So in the previous example, our range was between 0 and 2. And so those were the values that we allow, or where we chose our level curves to be. Here, I can put anything. So I'm going to start with, for example, 0, which is a point, because you're going to have 1/2. So I should have written it at z equals 0. Sort of. It's going to be 1/2 of x squared plus y squared. So that's going to give us just a point, because the only way you can add up to 0 with two non-negative numbers is if both of them are 0. So that level curve is just a point. We're going to do right now all the level curves first, and then we're going to put it in a 3D graph that is going to look beautiful, as you know. All right, so at z equals to 1, we realize that this, let's put 1 here. So 1, let's say that's what I did. 1/2 of x squared plus y squared, that's going to be the equation of an ellipse, if you think about it. And that ellipse is going to be in the x direction, you're going to have a 2. And then in the minus 2 rather, and a 2. And then in the y direction, you're going to have a 1. And your ellipse is going to go somewhere around here. Okay, so I'm going to go ahead and do another point. Z equals to 2. So that point 2 is equal to 1/2 of x squared plus y squared. And now you notice that if I divide everything by 2, the ellipse I obtain is going to be 1 equals 1/4. Oh, sorry about that. I want to make a note. If I divide by 2, I'm going to have this. And now I am going to go all the way to 2, which is going to be somewhere out here. Let's change the color. So the next curve is going to be out here. Now it's going to be 2 actually. And up here is going to be the square root of 2 for that ellipse. And so here's going to be 2, and then negative 2, and I get the next ellipse that's going to go here. And then if you would do at z equals to 3, then you would have, this would become 1/6, and this would become 1/3. So you'd have square root of 3 and then square root of 6. And so you keep getting ellipses that grow and grow and grow. Now let's draw that in 3 dimensions. And there's something else I'm going to introduce here, which is going to be vertical traces. So we're going to do that in a second. This is a good graph to do that. All right, so maybe I should have lowered it because I want to have, well, it's okay now. Did it. So at z equals to 0, I just have 1 point. I can plot that one. Even I can do that. Now at z equals to 1, so you're going to go up by 1. You're going to have an ellipse that is going to be longer in the x direction. So it's going to be elongated in the x direction. So something sort of like this. Let's claim that. Now at z equals to 2, you're going to go up again. You're going to have another ellipse that is going to be slightly longer as well. So somewhere out here, all the way to there. Oh, that one didn't come out as well as I wanted. Let's erase here. And do you see that the shape you're going to start forming? Oh, it should have been closer actually. This one is good. Of course, it's not drawn to scale, but if I would have drawn it to scale, then you would have ended up with something like this. And then at every step, you're going to be having ellipses that open, that give you this. But now, the interesting bit about this is that if now you were to fix, instead of fixing a value of z as we did, those are your level curves. If you were to fix the value of, say, x, so at x equals to 0, what happens is if you call this z, you get z equals y squared. So that is a parabola that opens in the yz plane. So you're going to have x equals to 0, so you're fixing the yz plane there, and there you're going to have a parabola that is going to go like here. Like so. So then you can also look at the parabola that you would have at z, or at x equals to 1, for example. At x equals to 1, you'd have another parabola that is going to be given by z equals 1/2 plus y squared, which is the same parabola we had here. It's just going to be shifted up. So somewhere here, we're going to have at x equals to 1. So when you pull forward here, you're going to have another parabola that is just going to be the same parabola, just shifted up. And I'm not even going to dare draw it because I know it's not going to look great. These are called vertical traces. So when you set values of x's or y's, those are going to be called your vertical traces. And what you're doing really is you're grabbing, as I drew here, you're grabbing the plane x equals to 0, and you're intersecting it with the curve. You're getting a parabola. Now, the next one, you would be grabbing this plane x equals to 1, and you're intersecting it with the parabola. That is going to give you a parabola that's going to be just a little bit higher on the graph. So you see, I'm afraid of drawing that because it's just going to make a mess. But that's really what you'll be doing. All right, so we're going to stop here the video for this topic, and the next video will be on limits. So thank you for watching, and I'll see you on the next one.